Ever wished we could, like, just shine a laser into space and launch stuff into orbit? Sounds like science fiction, right? But that's exactly what we're diving into today. You've been digging into this whole laser lightcraft thing, and honestly, it's blowing my mind.
It definitely captures the imagination. And the craziest part, it's not as far-fetched as it sounds. We're talking about propelling spacecraft with beams of light using lasers to literally ride shockwaves into orbit.
Okay, you're already blowing my mind.
Mm-hmm.
So where do we even start with this?
Oh.
I sent over that 2008 research paper, which felt seriously ahead of its time.
It is. That paper is a fantastic overview of laser lightcraft propulsion, and it highlights just how far back this concept goes. We're talking the 1960s alongside those early dreams of laser power. There's even a bizarre connection to the V-1 buzz bomb from World War II.
Hold up, you're saying there's a link between a World War II rocket and shooting satellites into space with lasers? Yeah. You've got to elaborate on that.
It's all about pulse detonation, which is basically a series of controlled explosions that propel something forward.
Okay.
The V-1 used pulses of burning fuel, but these lightcraft, as they're called, use pulses of laser-heated air. Imagine a focused beam of light creating mini explosions to push a spacecraft upward.
Okay, now I need to know exactly how this works. How do you build a spacecraft that can ride a laser beam? Are we talking some kind of futuristic light-absorbing material?
Not quite. Think of the lightcraft as a fat acorn with a mirrored bottom. This shape is crucial for what's called air-breathing mode, which is how it reaches hypersonic speeds within the atmosphere up to Mach 5.
Air breathing. So it's not even using onboard fuel at that point.
Exactly. That's the beauty of it. Up to a certain altitude, about 30 kilometers, the lightcraft uses the air around it as fuel. That pulsed infrared laser we mentioned, it's aimed at the mirrored bottom of the craft, focusing the energy inside to create plasma.
Plasma. We're talking superheated, electrically charged gas, right?
You got it. This plasma generates a shock wave, that mini explosion we were talking about, and this propels the craft upward. It's like surfing on light using those laser-triggered shock waves to climb through the atmosphere. And here's where that V-1 connection comes back in. The lightcraft's shape acts like an external compression chamber, much like the valves on that old pulse jet directing the plasma explosion for maximum thrust.
Wow, that's incredible.
Yeah.
But that only works within the atmosphere. What happens when the air thins out?
That's when the lightcraft switches to laser thermal rocket mode, still powered by the laser. But instead of air, it uses a small amount of onboard propellant, like a gas, or even a solid material like Delrin.
So it's like a two-stage system, but instead of ditching heavy rocket stages, it's switching propulsion methods. I'm guessing this is where the whole cheaper and more efficient argument comes into play.
Absolutely. Think about it. Single stage to orbit, minimal onboard fuel. That's a recipe for drastically reduced launch costs. Plus, you're not hauling around heavy combustion systems like traditional rockets need.
Okay, I need numbers. How much cheaper are we actually talking about?
Yeah.
Because right now, launching anything into space is prohibitively expensive.
Get ready for this. We could be looking at launch costs as low as $20 to $200 per kilogram of payload.
Wow.
That's orders of magnitude cheaper than the current industry standard of $10,000 per pound.
Wait, are you serious? That's like a 98% cost reduction. That would be absolutely revolutionary. We could launch so much more with that kind of efficiency.
Precisely. And it's not just about the cost savings. Imagine the environmental benefits of a launch system that doesn't rely on massive amounts of chemical propellants. Lightcraft technology could offer a cleaner alternative for accessing space.
Okay, this is starting to feel almost too good to be true. I have to imagine there are some major hurdles to overcome before we're all hitching rides to space on laser beams. What are the challenges holding this technology back?
You're right to be skeptical, because turning this incredible potential into a reality means tackling some significant engineering challenges. One of the biggest is something that might surprise you, Drag.
Drag. As in the resistance the lightcraft encounters while traveling through the air. I never would have thought of that as a major issue with the system powered by lasers.
It seems counterintuitive, but anything moving through the atmosphere, even a spacecraft riding a laser beam, experiences drag. And it can create a huge energy drain, especially at hypersonic speeds. In fact, the Air Force Research Laboratory study you shared highlights drag reduction as a critical design consideration.
So how do you even begin to address that? Are we talking about some kind of super aerodynamic design?
Exactly. Yeah. Remember how we talked about the lightcraft's shape being crucial? Well, researchers had to get incredibly innovative with that design. We're talking about meticulous shaping and refining to minimize drag as much as possible. It's not just about building a powerful laser, it's about ensuring the Lightcraft can efficiently slice through the atmosphere.
That's fascinating. So it's a delicate dance between the power of the laser and the aerodynamics of the craft itself. What other factors come into play?
Another huge factor is the laser's wavelength, basically the color of the light, even though we can't see these lasers with the naked eye. It turns out that wavelength has a massive impact on how efficiently the laser transmits power, especially over the long distances needed for space launches.
That makes sense. I remember from, high school physics that light can scatter and lose energy as it travels. So we want a laser wavelength that minimizes that energy loss, right?
Exactly. The study compared a longer wavelength CO2 laser to a shorter wavelength solid-state laser. And here's the catch-22. The shorter wavelengths transmitted power much more efficiently, like night and day difference. But
there's always a but, isn't there?
the technology for those super efficient, shorter wavelength lasers just isn't powerful enough yet. We're talking orders of magnitude difference in power output. It's like having a flashlight and needing a lighthouse.
Okay, so we've got drag, we've got the wavelength dilemma. This is starting to sound like a lot of roadblocks. What does all this mean for our dream of affordable space launches?
Oh, that's where things get really interesting.
Yeah.
Even with the current limitations, the Air Force Research Laboratory crunched some numbers, and the results are still pretty mind-blowing.
Okay, so give me the rundown. How much would it actually cost to launch something into space with this technology, even with those limitations?
They ran a cost analysis based on using the less efficient but currently more powerful CO2 laser.
Right.
For a small payload, about 12 pounds, they projected a launch cost of around $2,793.
Okay, that's more than that $20 a kilogram figure we were fantasizing about earlier.
It is, but remember that cost includes all the expenses involved: electricity, laser gases, cooling systems. And even with those costs factored in, we're still talking about roughly $532 per kilogram of payload.
Which, compared to the $10,000 per pound we're currently stuck with, is still an incredible leap.
Precisely. We're potentially talking about making space launches 40 times cheaper. And that's before we even solve the wavelength issue. Imagine if we could achieve that same cost efficiency with those super efficient, shorter wavelength lasers.
That's what has me so captivated by this whole thing. It feels like we're on the verge of a paradigm shift in space exploration, but it all hinges on those laser breakthroughs.
It's like we're holding a key to unlocking a door to a whole new era of space travel. And the implications are staggering. We could see routine, affordable access to space for research communication, even space tourism. It's not just about getting things into orbit, it's about what we can achieve when that journey becomes more accessible.
It's incredible to think about. Instead of billion-dollar satellites, we could have universities and small companies launching their own research projects into space. The scientific advancements alone would be incredible.
Exactly. It's about democratizing space exploration, making it possible for more people to contribute to our understanding of the universe. And that's why it's so important to keep an eye on laser technology, because those breakthroughs could happen sooner than we think.
So the takeaway here is clear. Laser technology holds the key to unlocking the future of space travel. If those breakthroughs materialize, the way we access and explore space might change more dramatically than we can even fathom.
It's a thrilling prospect, isn't it? The fusion of cutting-edge science engineering brilliance and a touch of audacious dreaming. And that's what makes this entire field so captivating. It reminds us that the future of space exploration is brimming with possibilities.
And on that note, we'll leave you to ponder the possibilities. It's been quite a journey diving into the world of laser lightcraft and the potential they hold for a future where space is no longer the final frontier, but a realm of unprecedented opportunity. Until next time, keep those minds curious and those imaginations ignited.